Hi, everyone. In this video, I will be demonstrating confirmatory factor analysis using an example by Whittaker and Schumacker in their 2022 book, A Beginner's Guide to Structural Equation Modeling. And whereas they demonstrated in their chapter how to perform the analysis using M+ and Literal, I'm going to be focusing in on a demonstration using Stata. So we're actually going to be using raw data from Holzinger and Swineford. This data is actually associated with the R package Psych Tools, so that's where I obtained a copy of the data. The data set contains 301 observations from 7th and 8th graders on various measures. We have visual perception, paragraph completion, sentence completion, and word meaning, and then there's cubes and this lozenges variable that you see. So as you look at the diagram on your screen, this is the basic confirmatory factor analysis model that Whittaker and Schumacker tested. And you'll notice that we have the visual perception, cubes, and lozenges. Those are indicators of the spatial ability factor. And we know that because we see that those variables are in rectangles. So in structural equation modeling, when you have boxes or rectangles, that represents a manifest or observed variable. And ovals represent latent variables or perhaps measurement errors. But as you can see right here, we have single-headed arrows pointing from the spatial ability factor to the visual perception, cubes, and lozenges variable. And so that's telling us that these variables are indicators of proposed indicators of this spatial ability factor. Then we see the paragraph completion, sentence completion, and word meaning essentially being treated as indicators of a verbal ability factor. So that's being reflected by the fact that we have arrows, single-headed arrows pointing from verbal ability to those variables. You'll see that on the right, there's a double-sided arrow or double-headed arrow connecting spatial ability and verbal ability, and that's representing the conceptualization that these factors are correlated. And then on the left, you see the little small circles with arrows pointing to each of the indicator variables, and that's representing measurement error. And that measurement error contains both unreliable or random measurement error, as well as certain specific variation that may be specific to those particular variables. So it may be systematic, but it's just been unmodeled in our CFA model. So we'll go ahead and open up Stata right here, and I actually have the data already imported. And I want to mention to you that you can obtain a copy of this data if you follow the link that's provided underneath the video description. So you can download a copy of the data to follow along. Also, I'm going to be focusing heavily on just the procedural aspects of a lot of carrying out this analysis, and also a couple of respecifications. And so there's a PowerPoint that I have linked underneath the video description as well that you can download that's going to provide a lot more detail conceptually and in terms of interpretation that I'm going to be actually going over in this video. I'm going to talk some about interpretation, but I'm not going to spend a lot of time on it because we're really just going to be focusing in on how to carry out this analysis using Stata. So what we have right here, we have our data set, and I'll show it to you really quickly. We'll go under data editor, and you can see there's our data right here, and these are the variables that we are working with. So I'm going to use the SEM builder by clicking on statistics. We'll go down to structural equation modeling tab right here, and model building and estimation. So when we click on that, our interface opens up, as you can see right here, and this is where we can draw out our model. So what we'll do is go ahead and go to the buttons on the left side of our interface here, and I'm going to click on the rectangle and go ahead and find a location in our interface here and just start clicking to represent our 6 indicator variables. So you have 1, 2, 3, 4, there's 5 and 6 right there. And next, I'm going to deselect that and click on the ovals and move this over as well so that we can basically represent our 2 latent variables. So there we go. And we'll deselect that as well. And at this point, I'll go ahead and specify the actual indicators. I'm going to link the rectangles with their respective measured variables. So I'm going to click on the first one right here, and we'll go down and we will select visual perception right here. Then I'll go to the next box and use a drop down here, and we'll select cubes. And then the next box, we'll select lozenges there. Then finally, we'll kind of wrap up with paragraph completion, sentence completion, and the word meaning right there. Now, in terms of the latent variables, the first one we're going to specify as spatial. So I'll go up to where you have this little, once I highlight the latent variable, I'm going to go up to the little box that says name, and I can type it in. I'm just going to type in spatial right here and then press enter, and you can see it shows up. And then we'll do the next one, which will be verbal. So at this point, we'll just type in verbal here and hit enter. And so now that shows up. So now we can draw in our paths from each of the latent variables to their respective indicators. So I'll select the add path button right here. I'll click on that and draw in the paths. So there we have verbal perception, there's cubes, there's this lozenges variable, there's the verbal ability to paragraph completion, sentence completion, and word meaning right there. And you can see that as we draw from the latent variables to those indicators, you see those measurement errors appear. So we have our error terms that are now included by default in the model. Next, we'll select the double-headed arrow button. We'll click on that, and then we will go ahead and draw that in. So I'm just going to draw from spatial to verbal right there. And now we have our double-headed arrow that's representing the association between spatial and verbal. So by default, if we run our analysis, by default, Stata is going to pick one of the indicators for each of those latent variables. It's going to pick one of those to be a reference indicator. And so the factor loading is going to be fixed to 1. And I talk a little bit more about that in that PowerPoint that I was telling you about. So I'm not going to spend any time on that, just to say that it's going to pick those reference indicators by default and set those factor loadings to 1. So the other factor loadings are going to be estimated in our model. So just to show you what I'm talking about, if I go up to estimation and click on estimate, you'll see that we have our method, maximum likelihood. There's also maximum likelihood with missing values. That's just basically full information maximum likelihood. We don't have any missing data right here, so that we don't really have to make a decision between the two. But I will say that if you select maximum likelihood and you happen to have missing data, then the approach to dealing with missing data is going to be list-wise deletion. So just kind of keep that in mind. So we'll click on OK right here, and it takes a second, but now you can see, looking at our diagram, that we have some factor loadings that are showing up. Now you'll notice, first off, you can see that the factor loading for the visual perception indicator, that is fixed to 1, and so also is the loading for paragraph completion in relation to the verbal ability factor. So what that's doing is it's scaling the latent factor. So it's giving it a measurement scale. Otherwise, we don't have any way of scaling those latent variables. And so if we didn't do that, if we didn't have any way of scaling those latent variables, then our model would not be identified and it wouldn't run. So there's actually a couple of ways that you can set the measurement scale of the latent variables. One is to fix a factor loading between a latent factor and a reference indicator to 1, and basically set that and then estimate the variance of that factor in relation to that indicator variable. Another might be instead to just simply set the variance of the latent factor to 1. So that's another option, but we're just going to stick with the more conventional approach right here. And in this particular case, we're setting the factor loading for our reference indicator to 1. So that's all that's going on. You'll notice too then that we have estimates basically unstandardized factor loadings for each of these other indicator variables. The other thing to note too is that when we look at the double-headed arrow right over here, we have this is basically the covariance then between our spatial ability variable or spatial ability factor and verbal ability. Now let's go ahead and go into our main interface and look at our output. First off, just kind of notice at the very top, we have basically the syntax that was generated from our specification using that SEM builder. So this would be an example of the syntax that we might write if we were typing it in directly. And so that's just kind of an FYI right there. You can see that when we scroll down, you'll see that we have our table of various coefficients and tests. So as you're looking at this, you'll notice that that at least with the our coefficient column right here, we have our fixed factor loadings right there for we have our verbal and spatial factors, and this is in relation to the visual perception and the paragraph completion indicator variables. You'll also notice as we're looking at this, we have our estimated factor loadings for spatial right here in relation to cubes. That factor loading is this right here, so it's 0.5589, and you can see that that is statistically significant. When we look at the loading for lozenges, you can see on the spatial factor, you can see that that is positive and statistically significant as well. So we have both of those loadings, both of them are positive and statistically significant. So again, cubes and lozenges, those are being treated as indicators of the latent factor spatial ability, and the visual perception is also being treated as an indicator, but we have fixed that loading to 1, or at least Stata did that by default. When we scroll down a little bit further, we can look at the loadings and tests associated with the verbal factor. So you can see right here, once again, the factor loading with respect to the paragraph completion indicator was fixed to 1. In terms of the factor loading with respect to sentence completion, you can see that we have a positive value right here, and you can see that it is statistically significant. In terms of word meaning right here, you can see that another positive value right here for that factor loading, and we have statistical significance. And I will mention too, just briefly, that you can reset the reference indicator in Stata if you wish. You don't have to let the program decide for you about which variable you're going to treat as an indicator or the reference indicator. And that's kind of important because, oftentimes we kind of let the program defaults make the choices. But ideally, what we would want is the scaling of the latent factors in relation to the best indicator, not just sort of arbitrarily choosing among those indicators. But again, most of the time, probably folks end up using the defaults, but that ideally, perhaps we would want to set the variances in relation to the best indicator. So if we wanted to do that, just to show you really quickly, if I go back into this SEM builder, if I kind of click on clear estimates right here, I could set, let's say cubes, if I wanted to set that as my reference indicator, I can click on that arrow right there, select it, and then up here at the top, you'll see there's a little beta. I can type 1 and then enter, and you can see that that would fix that fixed cubes as a reference indicator, and that factor loading would be fixed to 1, and then the others would be estimated. So I'm just letting you know that. I'm actually going to get rid of that because I'm just going to stick with the main defaults as we go through this particular demonstration. So the other things to kind of pay attention to, if you look down below, you'll see that we have the variances for our measurement errors. So all of these right here, these are referring to the variances of the measurement errors. So these are the actual variance estimates themselves. You'll see here in this part, we have the variances associated with the latent variables right there. And then at the very bottom, you'll see that we have the covariance between spatial ability and verbal ability. So this is the covariance between the two, and you can see it's positive and statistically significant. Now, something else that you might want to do is to basically get information concerning the variation in each of the indicators that's accounted for by the factors. And so in conventional factor analytic terminology, basically that is referring to the communalities. So we can obtain that information pretty easily. We can go to the command line down here, and in that line we can type estat and then EQGOF, and that's for equation goodness of fit, or equation level goodness of fit. When we press enter, you'll see that we get R-squared values, which is going to represent for each of our indicator variables the proportion of variation accounted for by the factors. And because each of our items are loaded onto a single factor, this would basically reflect the proportion of variation accounted for by their respective factors. And keep in mind that the basic idea is that when we had those arrows pointing from the latent variables to those indicator variables, the idea is that the variation in those indicator variables is being accounted for by the latent factors, and that's why we have the R-square values associated with each of these. So as we're looking at this, you can see that the R-square for the visual perception variable right here is 0.605. So basically that first factor is accounting for about roughly 61% of the variation in visual perception. Then for cubes, you can see that it's 0.18, roughly 0.186. So that first factor is accounting for about almost 19% of the variation. Then for lozenges, you can see right here, that factor is accounting for about 32% of the variation. And then you can see for that second factor, that verbal ability factor, it's accounting for more consistent amounts of variation in its three indicators. Basically between about 70% and roughly 73% of the variation in those indicators. Okay, so in addition to looking at the R-squared values associated with each of our indicator variables, we also are going to want to look at the overall fit of our model. And so we're going to generate goodness of fit statistics, and we can do that in the command line by typing estat and then GOF, comma, and then we're going to type in stats, and then inside parenthesis we'll type all. So I'll hit enter, and now we get our goodness of fit statistics. So as you can see right here, we have at the top, we've got the likelihood, basically the chi-square goodness of fit test, which we have the test value right here and the p-value, basically our significance test. And the basic idea with this test is we're testing the discrepancy between our sample covariance matrix and our model implied covariance matrix. The idea is that the less discrepancy, the better. And the greater discrepancy, that's going to indicate more model misspecification. So if we find statistical significance, that's actually regarded as an indication of discrepancy and lack of fit. And so as you can see right here with the chi-square test, we see that the p-value is 0.002, suggesting a significant difference between our model implied and sample covariance matrices. Now, because the chi-square test is so heavily impacted by sample size, and given that SEM and which incorporates CFA is a large sample technique, oftentimes what you can have is you can have minor discrepancies and still find statistical significance because it's a large sample technique. And so as a result, we don't tend to just focus our attention on that chi-square test. We tend to look at other indicators and to provide us a more global picture about the fit. And so other indicators that we might consult include the RMSEA, which is the root mean square error of approximation. And you can see right here, our value is 0.083. So in terms of thinking about conventions for evaluating the fit of our model based on that, you could think about it this way, that values that fall between 0 and 0.05 would be an indication of close fit. Then values that fall between 0.05 and 0.08 would be considered acceptable fit. Then you might say that values that fall between, say, 0.08 and 0.10 might be considered more mediocre fit. And then values that fall that are basically, 0.10 or above would be regarded as indicating poor fit. So you can see, looking at our RMSEA right here, that our fit is not looking all that great in this particular case. So looking at that, and also looking at the chi-square test, you can see that we have some indication that this is not really the greatest model. The other thing to kind of note too, as we're looking at this, we'll take a quick look at this p-close test. And this is basically a test of our RMSEA against what we would expect if under, with the idea that we have a close fit. So we're looking at the discrepancy between our RMSEA and what we would ideally have with close fit. And so if that p-value, if it's that's presented right here, if this is, say, less than 0.05, then we would be rejecting the null hypothesis of close fit and essentially concluding that there's not close fit of our model to the data. If the p close value is greater than 0.05, then we would not reject the close fit null hypothesis. And you can see right here that that actually seems to be the case. So we do have some positive news in the form of our p-close test. Then when we look at our CFI and TLI, these two indices right here, basically conventional values, I guess you could say, that at least an acceptable fitting model would have a TLI and CFI value that would be maybe around 0.90 or greater. And if we get up into the area of about 0.95 or greater, in that particular case, we're kind of more into the superior levels of fit, I guess you could say. So keep in mind that the theoretical range for these indices is 0 to 1, even though we can still have values that might fall outside that. So the closer we are to 1, the better. And as you can see right here, both of these indices are suggesting good fit. So we have the p-close test that's giving us some good indications. We have the CFI and TLI, which are giving us some good indications. And then if we look at the SRMR, you can see that that value is 0.047. So in terms of assessing this, basically a value of 0 would suggest, I'll just say, perfect fit right there. And then values up to, let's say 0 to a little bit higher than 0 to 0.05 would suggest good fit. And then values that fall in the range of 0.05 to 0.10 would still be considered acceptable. And I'm kind of pivoting off of the discussion by Whittaker and Schumacker in their text. So looking at that, you can see that we have some evidence of at least reasonably good fit here. The same goes then for our CFI and TLI. We're in good, reasonably good shape with the p-close test, but we still have this RMSEA and also the chi-square test. So we have a little bit of a mixed bag in terms of evaluating the overall fit of our model. It's not the worst fit that we could see, but it's also not perhaps the best fit. So we might think about looking at other various indicators that would suggest where the model might be misspecified, and then consider maybe some model respecification. Just keeping in mind that as we think about looking at potential sources of misspecification, we also want to not just simply respecify a model based on empirical criteria, but also think in terms of does it make sense from a conceptual standpoint? And we don't want to just over parameterize our model. We don't want to add in just a lot of different parameters just because various indices might suggest that. Rather, we want to be choosy. We want to have a conceptually relevant model, but one that's also parsimonious. So one way that we can do that is to generate model fit indices, or excuse me, not model fit indices, modification indices. So to do that, if we go down to the command line, we can type in estat and then MINDICES. So basically M indices. So when I press enter right here, you can see that we get some modification indices right here. And essentially what we can look at, these are essentially kind of recommendations, for lack of a better way of putting it, or suggestions for what parameters that you might add into the model that might result in a decrease in the chi-square value. And with that chi-square goodness of fit test value, keep in mind that if we have a perfect fitting model, that value is going to be 0. And then as the chi-square value gets larger and larger, that's going to represent greater and greater levels of lack of fit. So if you think about it, these indices, particularly the modification indices, what they're basically getting at is the change in chi-square in terms of decrease as a result of adding in parameters. So it's kind of an approximate decrease in the chi-square as a result of adding in certain parameters. So you'll see that we have the modification index right here, and then you also have a significance test. So you have the degrees of freedom, and then you've got the p-values to represent basically it's a significance test. So what we're looking for are those modification indices that are larger and that would be significant, and those would be reflecting kind of candidates for possible respecification. So as you're looking at this right here, we've got our verbal factor, and you'll see that one of the larger numbers in terms of modification indices is this one right here, the 10.433. And what you have is this suggestion that perhaps we incorporate a path from the verbal ability factor to visual perception. We already have spatial ability, a path from spatial ability to verbal perception, but now it's saying, well, we could also perhaps add in another path from verbal ability to visual perception, and this might improve the fit of our model. And you can see too that we have, in terms of the significance, you can see that there's that's assumed that there might be a significant decrease in the chi-square value as a result of adding in that path. So that's one possible suggestion right there. You also have another one. If we look at this one right here, this is another one in terms of the factor loadings. We could add in a path from verbal to lozenges right here, and that would suggest perhaps a decrease in the chi-square value and a significant change as well. So as we look through all of these, that's basically how it's kind of done. You can also see down below, you've got suggested covariances between measurement errors. So you'll notice that, for instance, the largest modification index value is this one right here, and that's suggesting a potential covariance between the cubes and lozenges indicators. And so you'll also see too that expected change would be statistically significant. The change in fit would be significant. And as you're thinking about the error, the measurement errors associated with these indicator variables, you have to sort of think about, well, why might there be correlations in between those errors? One possibility could be that there's maybe some unspecified factor, some factor that's not been included in the model that might partially account for that relationship between these variables. So it might be another theoretically relevant factor, or it could even be something like measurement artifacts that are common to those particular indicators that might produce part of the association between those two variables. So you have to kind of think about why you might want to add in that particular covariance if you just indeed decide to do that. So what we're going to do now, and I will mention too that there's another approach to kind of looking at some of these things, which is to look at residual matrices, and I kind of discussed that in that PowerPoint. So I'm just going to kind of move on at this point and move to kind of the next step that Whittaker and Schumacker used, which was to add in that covariance between the the measurement error for cubes and lozenges. So we'll go back into our path builder or SEM builder right here, and we're going to add in that covariance. And it's really pretty easy to do. We'll click on this button for add covariance right there, and I'm going to draw up from lozenges to cubes right there. And so now we have specified that particular covariance. And so now we can run the model where we've allowed that relationship to become manifest. So at this point, what we'll do is go ahead and click on estimation and click estimate, and we'll go ahead and click on OK there. And so now you can see we have our estimates for this model. Remember that these are all unstandardized estimates in our model. And so you'll notice that the covariance in between cubes and lozenges, that's this value right here. And if we go into our main interface, we can get a little bit more detail about the tests of these different parameters. I'm not going to go through everything as I've done before, but I will kind of go down here and just highlight the covariance between the measurement errors for cubes and lozenges. So here's our covariance right there, and you can see it's positive and statistically significant. So there seems to be some factor outside of the model that's contributing to the association between those two variables, aside from just whatever factor is associated with them. So the other thing I want to draw your attention to as well is that right now we've just been focusing mainly in on the unstandardized loadings, but if we can go under estimation right here and click on estimate, if we go to reporting and click on display standardized coefficients and values and click on OK, then in this particular case, now we have a standardized solution. So as we're looking at this particular solution, these factor loadings that you see right here can be interpreted as correlations between the latent factors and their respective indicator variables. So a lot of times when people are reporting, if they want to offer a little bit more substantive interpretation of the relationships between the indicators and the latent factors, a lot of times they tend to gravitate towards reporting on the standardized coefficients because they are representing correlations between the factors and the indicators. And that's really more of what we're oftentimes used to because most of the time when we're carrying out exploratory factor analysis and we're interpreting loading matrices, those are at least the structure coefficients are presented as correlations between the indicators and those latent variables. Now, as we're looking at this value right here, this is now the correlation between the spatial ability factor and the verbal ability factor. And then as we look at this relationship right here, this would be interpreted as a correlation between the measurement errors for cubes and lozenges. So let's go ahead and we'll go into the main interface here. And so now you can see all of our results are presented. You can see up here it says standardized. So now you can see there's our standardized coefficients. In terms of the spatial ability factor right here, we have our standardized factor loadings for visual perception, for cubes, for lozenges right there. You also see that we have our significance tests as well. You can see all of those are statistically significant. When we scroll down a little bit, you can see the standardized loadings for with respect to the verbal ability factors. So for paragraph completion right here, there's our loading. You can see it's significant. For sentence completion right here, we have our standardized coefficient, basically a correlation, and that's significant. And then for word meaning right here, you can see it's also basically positive and significant there. As we look to, if we scroll down a little bit further, we can look at the, again, these are the measurement errors that you see right here. And so you could think about these as 1 minus the communality estimate. And so in other words, if we go in and we generate that equation level goodness of fit, basically the 1 minus the R² value is going to be equivalent to this if we were looking at the standardized estimates. You'll also notice too that the variances of the spatial ability and verbal ability factors, both of those are fixed to 1. And if we look at the where it says covariance E cubes and E dot lozenges right there. This is actually because this is their standardized output. That's the correlation between the two variables, and you can see it's significant. The correlation between the spatial ability factor and verbal ability factor is 0.419, and you can see that that is statistically significant as well. If we, as I said before, we can generate those R-square values very easily just by typing in E-stat, and then we can type in EQGOF for equation level goodness of fit. And now you can see we have the R-square values that are showing up right here in our output. So in this column right here, associated with each of our indicator variables. So at this point, let's go ahead and take a quick look at the overall model fit. We'll go down to the command line. We'll type in E-stat, so then GOF, then stats, and inside our parenthesis all, and hit enter. And so now as we're looking at this, you can see that in terms of the chi-square goodness of fit value, it's now down to 13.972, and the p-value is 0.052. So if we're going to be very literal about the 0.05 threshold, we would say, well, that it's not significant. So that's, it's basically suggesting that, we have it's certainly not significant at the 0.05 level, but certainly kind of near significant. But again, I'm not going to spend much time thinking about that particular issue in and of itself, because again, this test is affected by the overall sample size, and so we want to still be looking at a lot of those other fit indices. So if we look at the RMSEA, you can see it's 0.058, so that's certainly better than what we had before. So this would definitely put us in the acceptable range right there. So you can also see that the p-close test right here is 0.336. Again, that's putting us, that's suggesting, both of these are suggesting that we have a reasonably good fitting model right there. When we look at the CFI and TLI, both of those are higher than what we saw before, and both of those are really indicating much more superior fit, for lack of a better way of putting it. And then you can see the SRMR is 0.033. So again, all of this taken together is suggesting definitely a better fitting model than what we had previously. Okay, so that's going to pretty much wrap up this discussion on CFA with Stata. As I kind of mentioned earlier, be sure to check out the PowerPoint. Just go to the link underneath the video description, download a copy of the PowerPoint. There's a lot more detail and discussion than I've really gone through in this video, but hopefully you find it useful, and I appreciate you watching.